Hello, welcome back. Today we're going to be looking at some Euclidean geometry questions. The question reads, in the diagram PQRS is a cyclic quadrilateral with RQ equals RS, ST is a tangent to the circle at S, SR is produced to N, R2 is equal to 68 degrees. Determine with reasons the size of angle P. Okay, so we can see here that this is a cyclic quadrilateral. This is the exterior angle of the cyclic quadrilateral. So we know the theorem that the exterior angle of a cyclic quad is equal to the interior opposite. So P is going to equal to 68 degrees. So they want to know what is Q1 and what is S1. Okay, so Q1 we can work out quite easily because remember that is a straight line, which means that R1 is going to equal 180 minus 68. So that's 112. And since this line is equal to this line, it means that these angles are going to be equal. So we can work them out. So 180 minus 112, then divide that by 2. That means this is going to be 34 degrees and this is going to be 34 degrees. Then they want to know what is S1. So S1 is this angle right here. And importantly, they tell us that ST is a tangent. So this angle right here is the angle that the tangent makes with the chord. And we can use tangent-chord theorem. That means it's going to equal to this angle right here. So S1 is going to equal 34 degrees as well. All right, let's move on. In the diagram, AB is a diameter of the circle with center F. Okay, AB and CD intersect at G, FD and FC are drawn. BA bisects CAD, D1 is 37. So this is important here, BA bisects CAD. What does that mean? It means that this is equal to this. D1 is 37. Okay, determine giving reasons any three other angles equal to D1. All right, so what we can do here is let's construct an imaginary line here. And that's going to be my focal point for this. So that's my line, that's my chord. And then we can use angles in the same segment. So from here, we can see that A2 is going to be 37 degrees. And we just said that A2 and A1 are equal. That means that's going to be 37 degrees as well. Okay, now while we're at it, let's try and work out more angles. So we know that FD, FC, and FA are all radii. So that means that this line is equal to that line is equal to that line. So that means that D3 is going to be 37 degrees. C2 is also going to be 37 degrees. So we've got whole much more than 3 angles that equal to D1. Okay, next one, show that DG is equal to GC. So show that this line here is equal to that line right there. Okay, not a problem, we can do that. So what we'll do first is let's work out what this angle here is. So we'll use some angles in a triangle. So 180 minus 37 minus 37, that's 106. So this is 106. That means this also is going to be 106 because they're the same triangles. Now what we can do is we can use a theorem. So this is the angle at center. And that's going to be double the angle at the circumference. So there. So this angle B is going to be half of the 106. So divide that by 2. That's going to mean that this is 53. Okay. That means angle G, this angle right here, is going to be 180 minus 53 minus 37, that's 90. That's going to be 90 degrees. So that means this is perpendicular, that's perpendicular. And we know the theorem that says that a line drawn from the center, if it's perpendicular to the chord, then it will bisect the chord. And so we've shown it. Next question, if it is further given that the radius of the circle is 20 units, calculate the length of BG. All right, so the length of the radius. So that means that this is 20, that's 20, that's going to be 20. They want BG, so let's call that X. And that would then mean that this portion here would be 20 minus X. Now what I want to do is I just want to quickly focus on this triangle right here. That is a right angle triangle. Let's draw it out here on the side. So there, there, and there. We said that that is 20 minus X. We said this is 20, and this angle, oh, we do need an angle, but we can work out this interior angle right here. If that's 106, then that's going to be 180 minus. So 180 minus 106, that's 74. So let's insert that here. So this is 74 degrees. Now we can use a trig function or a trig ratio. This right here is the hypotenuse. This is adjacent, so we can use cos. So we'll say that cos of 74 degrees is equal to 20 minus x divided by 20. Now we multiply. So 20 times cos of 74, that's 5,51 equals 20 minus x. That means x is equal to 20 minus that, which is 14,49 units. Okay, that's it. Let's move on to the last question. And this question reads, in the diagram, COD is the diameter of the circle with center O. EA is a tangent to the circle at F. AO is perpendicular to CE. Diameter COD produced intersects the tangent to the circle at E. OB produced intersects the tangent to the circle at F. CF intersects OB in T. CB, BD, OF, and FD are drawn. A lot of information there. We've been given this complex looking diagram. Let's go through some of the questions. So the question says, prove that TODF is a cyclic quadrilateral. So let's look for TODF. Okay, now we think of the properties of a cyclic quadrilateral. Some of the properties, the opposite angles are supplementary. Exterior angle equals the interior opposite. We can look for the angles in the same segment or the converse of it. A lot of different ways, but let's see what we have. So we know that this line right here, that's my diameter. And so if I complete this, that's angles in a semicircle. That means that that angle is 90 degrees. So this right here is going to be 90 degrees because angles in a semicircle. Then, because that's 90 degrees, this right here is going to be 90 degrees. And so we've proven now that it's a cyclic quad because the interior, the sum of the opposite angles is 180. Let's move on. Next question. Let's actually clear this up a bit. Next question reads, prove that D3. So D3 is this angle here. Prove that it's equal to T1. Okay, actually we do need that cyclic quad here. So what we can do here is we can say that this is the exterior angle of a cyclic quad. It's going to equal the interior opposite, so it's going to equal this angle right here. And because of vertically opposite angles, those are going to equal each other. So basically what we need to write here is we'll say that D3 is equal to T3, and then T3 is equal to T1. Therefore, D3 is equal to T1. Of course, the reasons again, exterior angle is equal to the interior opposite, and then vertically opposite angles. All right, now what I'll do is I'm going to just color code this. So that is equal to that, which is equal to that. Okay, next question. Prove that triangle TFO is similar to triangle DFE. Let's highlight them. So TFO is this right here, and then DFE is this one. So what we can do is we'll start by saying, so in triangle TFO and triangle DFE, we will say that T3 is equal to D3, and that was proven in the previous question. So that's my first statement. Now we need to show why angle F here is equal to angle F here. So in other words, we need to show why F4 is going to equal to F2. Now the way we can do this is, remember from the beginning we said that this right here is 90 degrees. And because EFA is a tangent, this right here is going to be 90 degrees. So how does that play out? So this is going to be, let me just clear this because I can't see. That's 1, that's 2. And I think that's 4. Was it 4? Yep. Okay. So 2 and then 4. So my statements are going to be here that F2 plus F3 is 90 degrees. Okay? And we proved this in the first question. Then F3 plus F4 is equal to 90 degrees, and that's because the radius is perpendicular to the tangent. That means that F2 plus F3 is equal to F3 plus F4. So F3 can cancel. That means my next statement is going to state that F2 is equal to F4. Now we can then show the last point. So let's just color that in and color that in, so we know that those are equal. And then that would mean that E here would equal O here. So let's write that down. O2 is equal to angle E, and that's going to be some angles in a triangle. Okay, and then we can say therefore TFO, or triangle TFO, is similar to triangle DFE. Okay, let's move on. If B2 is equal to E, prove that DB is parallel to EA. Okay, if B2 is equal to E, so where is B2? So B2 is this here. B2 is equal to E, so that should be green. If that's green, prove that it's parallel. So prove that these lines are parallel. Okay, let's again clear up some space because there's a lot of colors and stuff here. So there we go. Like so. And we want to show that this is parallel to that. Okay, not a problem. What we can do here is we can say that this line is a radius and that line is a radius, so that this triangle must be isosceles. And if it's isosceles, it would then mean that D1 is also going to be equal B2. So let's color that in, and that's going to be green. And then the last thing is, we can see that they're going to be corresponding angles because there is a letter F here. There's the letter F, like so. I can just show it to you like this. All right. So we've shown that they're parallel. Let's neaten this up a bit now. So that is parallel to that. Okay, and then on to the last question. Prove that DO is equal to TO times FE all over AB. And this is a bit of a tricky one. So let's go through it together. Now, usually when you get these kinds of questions, you do need to go back and use the stuff that you've already proven before. So in this case, I'm going to use 10.3. So from this similarity, I can get some ratios. And the ratios are going to be TF divided by DF is going to equal TO divided by DE, which is going to equal FO divided by FE. Now, if I look at the question has TO here, and then I have TO right here. Then the question has DO, right? But I know that DO and FO, so here, see, DO and FO are the same because they are radii. So instead of that, I can say that that and that is the same. So that means I'm focusing on these. All right, so let's focus on that. So TO over DE is equal to FO over FE. Now, we said before that DO and FO are equal in length. So let me replace that. So TO over DE is equal to DO over FE. And remember, we said that they are equal because they are radii. Okay, so we're making some progress. Now what we can do is, we want to take this across there. So we're going to get TO times FE divided by DE is equal to DO. So let's look at what we have. So we have the DO here, we have the DO here. We have the TO times the FE, we have the TO times the FE. Now all we need is we need to replace DE with AB. And we can't just change it. We need to figure out why we can change it, or why would they be equal. So we want to know why this line here can be replaced with that line right there. Now, it may be easy to some of you, but let me show you why. So what we need to do here is focus on this triangle right here. These two triangles. Now, because this line is parallel to that line, those triangles are going to be similar. So triangle ODB is going to be similar to triangle OEA. And from here, we can get some ratios. And the ratios we're going to focus on is going to be OD and DE. So OD divided by DE is going to equal OB divided by BA. Now let's switch this. So we'll switch these. So OD divided by OB is going to be DE divided by BA. Now OD and OB are radii, so they are equal to each other. So the ratio here is 1. So DE over BA is equal to 1, which means that DE and BA must be equal to each other. So since now we've shown that, we can replace DE with AB. And we are done. Thank you for watching, and I'll see you in the next one. Bye-bye.